Hello guys, and welcome to this fourth video on our series on numbers. The subunit is going to be on sets, Venn diagrams, and number systems or number types. Okay, this is going to be related to eWorkbook number 4, which I'm going to include in the comment section below. So please take a look at that, and the questions related to this subtopic are going to be in there. Okay, let's begin. Normally, when we are brought into this world, when we are born, or if you like, brought into the world by the proverbial stork, our brains start to pair up things. All right. So as you see your surrounding, there is a tendency for us to start grouping things or categorizing things depending on how they look like. All right. So after a while, a baby who has been in the house for a long time and has been used to seeing the domestic animals or pets is likely to make a mistake when they go out and they see a cow for the first time, and the most likely reason is because while they are inside and they're used to seeing a cat, the cat has got 4 legs, the cat is hairy, and so anything else that they see around them that has got 4 legs, the baby is bound to start thinking that is a cat. All right? So no matter what, we tend to start grouping things, giving them names according to certain properties that they possess. All right, so this is what we do, but sooner or later we are able to start giving them the right name. So we are able to start saying, telling whether an object is an animal, it is a living thing or an unliving thing, is it a plant, is it a flower. We are able to start categorizing them correctly into the different types of things that they may be. So when we categorize them, we do so by giving them a particular name, a name that relates to a property that they all share. So when we look at insects, for example, there is something that they all share. It could be that they have 6 legs, or they fly, or one of them, they have antenna, and so on, right? But later, as we get into higher school, Grundschule into high school, we are better able to categorize the things around us better. So we will be able to tell what animals are and which ones fall under plants and which ones are fungi and so on. So there are certain properties that they will possess that make them fall into the different categories of the living things or the non-living organisms, right? If you're a chemistry student, you start seeing the different elements in the periodic table, and you're able to group them into certain patterns depending on certain properties they have. Group 1 elements have a single electron in the outermost shell, for example, and so on, right? But the same thing that we do with living things and with plants and in chemistry is the same thing we do in mathematics with the numbers. So all numbers are categorized, are referred to as complex numbers, if you may. And complex numbers come into 2 sets, one of which are the real numbers and the other one being the imaginary numbers. So we can classify numbers into 2 broad types, real numbers and imaginary numbers. The real numbers, we will leave the imaginary numbers for a while. We will look at this later, but let's just concentrate on real numbers, which we have met for most of our life at this stage. Okay, so the real numbers, we can group them or categorize them or classify them into 2 types, which are rational numbers. We will talk about what this means, and the others are irrational numbers. But while we are at it, we can describe the rational numbers themselves. So rational numbers, we have integers, we have fractions, and we also have decimal numbers. While and under integers, you have 0, you have numbers that are categorized, are considered negative, others that we refer to as being positive. We have numbers that we call even, and others that we refer to as being odd, and we have prime numbers. In the case of fractions, we've looked at this in the section on fractions. We have proper fractions, mixed fraction, improper fraction. So these are all different ways in which we can categorize numbers, right? We can classify numbers. We have decimals, which will fall under recurring decimals and terminating or terminal numbers, okay? A terminating decimal is any decimal that ends. So 0.25 is a terminating decimal because it ends at 5, 0.25, okay? On the other hand, we have irrational numbers, and irrational numbers are those that cannot be expressed as fractions. So rational numbers can be expressed as fraction. Irrational means cannot be expressed as ratios, okay, or as fractions. And some of those numbers are like pi, transcendental numbers. Pi is an example of a transcendental number. E is a transcendental number. Pi is 3.1415 something, so it never ends, it continues, the decimals continue to infinity and do not repeat themselves. The number E is 2.718 something, so that also continues to infinity, non-recurring, non-terminating, okay? The phi you see there refers to something called the golden ratio, 1.618, and again that's a recurring decimal that is non-terminating and non-ending, okay? Non-terminating and non-recurring, all right? And then we have irrational numbers that fall under the real algebraic numbers. So the square root of 3, 1.732, and so on continues to infinity, non-recurring, non-terminating, is an irrational number. Root 2 plus 1, I think, is about, 2.4142 or something like that. Again, that continues to infinity, non-terminating, non-recurring. So these are referred to as irrational numbers, okay? So broadly, numbers can also be categorized, can be split up into different classes or different categories or different groupings, okay? And this we do naturally as human beings. We tend to look at things around us and then group them into certain properties that they possess. So if we're going to refer to a number as being prime, there must be a property it possesses that the others do not have, right? Or a particular property that this as a group of numbers will have that the other numbers may not have, okay? If we say fractions are improper, there must be something that a way in which they look that other types of fraction do not look like, all right? So this is what we do with the numbers. So let's get into what has brought us into this. So while in other subject areas we refer to these as groups, we group things, we put things into groups, or we put things into classes. All right. On the other hand, in mathematics, we don't use the term groups or classes. Instead, we prefer to say sets. Okay. So the term groups or the term classes, we replace that with the term set. So a set of numbers refers to a group of numbers that share a certain property. Okay. So by definition, we can say that a set is a collection of things, usually numbers or objects, that share a common property, okay? That is how we define a set. So in mathematics, we will not say a group of numbers, we will not say class of numbers, we will say a set of numbers, okay? Let's see. Try to describe the common property shared by the elements of this set. So consider this as elements of a set, or that this is a set. What common property do all these elements or these members of the set share? Please pause the video and think about what the answer might be. Okay, well, these are plants. So the first thing is, of course, being plants, we know they share the name plant. They have leaves. You could say they have leaves. Some of them have stems. They grow from the ground and so on. So those are examples of the properties or a behavior or a characteristic of the members of this group or the members of this set. Okay, here is another one. Look at that carefully, pause the video and think about what is common to this set. Okay, you could say that this is the set of logos used by different cars. So being a car is a common property to all of this. You could say these are companies, these are logos for the companies that sell cars or manufacture and sell cars, and so on. Okay, here's another one. What kind of set, what common property do elements or the members of this set share in common? Well, these are, you could say, the logos as used by social media. Okay, so all of them are social media logos. Okay, you could think of something else, but that's pretty one of them. And what about this one? You could say these are cutlery, related to food, related to a table, and so on. So basically, any property that each of these elements or these objects share would be referred to as a common property, right? Here is another one. Look at this. This is called the Pascal's triangle. I have shaded all the other numbers and left some in white. Could you pause the video and think about a property that is common to all the numbers that are in white? There is a 2 there, there is a 4, there is a 6, there is 10 and 20, and so on. Could you think of some common property for the numbers that are in the white sections or in the white boxes? Pause the video and think about it before I give you your answer. Well, if you look at them carefully, you should notice that these are all even numbers. So if we shaded all the even numbers on the Pascal triangle, this is the pattern you'd see on the triangle. We'll discuss Pascal's triangle later, but right now, just think of it, know that this is Pascal triangle. You find the different numbers by adding the 2 numbers in the boxes above. So if you add the numbers in the boxes above, you get the number directly below them. So we have 2 and 1 somewhere here. So if you add 2 there and 1, you get the 3 directly below them. So look at that. All of the numbers are found by adding the 2 numbers, the numbers in the 2 boxes directly above it. Okay, and that forms the Pascal's triangle. We use the Pascal triangle when we are expanding a binomial expression. If we wanted to find x power 3, for example, if I wanted to find x or a plus b, let me use a different color. If I wanted to find a plus b, everything to the power of, let's say, 4, then I can use the Pascal's triangle. If it is power 4, then I'm going to the line number of this line here. So this line there, this line here, will give me the coefficients. So I will write this as a power 4 plus 4 a power 3 b plus 6 a squared b squared plus 4 a b squared plus b power, am I right? Power 3, power 2, power 4, yes, I am right. And this is going to be b, this is supposed to be b power 4, power 2, this is power 3, and so b power 4 like that. So if I expanded this the long way, I will end up here. But because I have Pascal triangle next to me, I can find this expansion without wasting too much time trying to expand that. How did I get these values? You should be able to see this is a power 4, the next term is a power 3, then a power 2, a power 1, a power 0, and b power 0 here, b power 1. So the powers of b are increasing as we go along the terms, and the powers of a are decreasing as we go down. And the coefficients here is 1, this is 4, this is 6, this is 4, that is 1, which is the same thing as what you see on the Pascal triangle there. Okay, so this is how we do this. But it's not a big deal right now. We're not really very keen on the Pascal triangle right now, so don't worry about this. When the time comes, we will discuss it. So the Pascal triangle can help us find so many different types of numbers, usually number sequences. So you can see that's the pattern, as we've said, that we get when we shade off, or when we leave out, we shade everything and leave out all the even numbers or multiples of 2. Okay, I have placed an Excel spreadsheet that contains the Pascal's triangle. Please use that Pascal's triangle. Use the spreadsheet to try and shade other number patterns. For example, how would the pattern look like if we shaded all the multiples of 3, or all the odd numbers, or all the prime numbers? Will there be some pattern that we form when we do that? Okay, here's another one that we get if we shade all the multiples of 5, for example. The shape now looks like that. You can see the patterns are different from those patterns there. So you can try different ones, play around with the Pascal's triangle and see the different kind of patterns you get when you shade numbers that share some common properties, right? So these are multiples of 2 and these are multiples of 5. You can see they are multiples of 5. The first one there is 5, 10 and so on. So what about multiples of 3? What about multiples of 4? What about odd numbers and so on? So try numbers with different properties and see how they look on the Pascal's triangle, okay? Okay, we want to start defining some of the terms. One of the terms we want to define is what we mean by the element of a set. So each member in a set is referred to as the element of that set. Okay, the symbol we use to identify elements is that looks like an E facing the other side, right? So that is used to represent the symbol that we use to represent elements of a set. So if you want to write that A is an element of a set, we would write A and write that to indicate element, and then we'll write the correct set that we are referring to. All right. We also use this kind of squiggly brackets called braces to enclose members or elements of a set. So for example, if for example set A is such that it contains 1, 3, 5, 7, and 9. First of all, we need to be able to describe this set. Unfortunately, I've shown that, but this can be described as the set of odd numbers that lie between 0 and 10. So all these are odd numbers, as you can see. All right. The squiggly lines, the squiggly brackets, as you can see, help us identify this as a set, as opposed to being the coordinates of a point, for example. All right. So in this case, we can say that 5 is an element because it's an object in the set A. We can say that 5 is an element of set A. Okay. 3 is also an element of set A. 9 is an element of set A. On the other hand, 2 and 8 are not inside this set, so 2 and 8 are not elements of the set. Mathematically, we can write this by saying 2. So remember the symbol for element. So we want to say that 2 is 3 rather. We want to say that 5 or 3 or 7 or 9 are elements of set A. Then we will write that like this, that 5 is an element of A. So when you see that, you read that as 5 is an element of set A. Okay? On the other hand, how do we show that an element such as 2 is not in the set A? We write 2 and 8 are not elements. So that line indicates that 2 and 8 are not elements of set A. Okay? Here's an example. Look at these objects as elements of a set, right? The property common among the elements of this set, these are animals. Think of a property that is common to these. You could say they all have a tail. You could say that they all are hairy, or they have an ear, or they are animals, and so on, right? Wild animals, or whatever it is you come up with. So all those would be examples of a common property members of the set will share. So they all have hair, or they are furred. You could say they each have they have a tail, or that they are four-legged, they have ears, and so on. Okay, those are some properties that all the elements of the set share. Yeah. Next, we want to define cardinality. So the cardinality of a set refers to the number of elements in the set. Okay, so we know what a set is. We know what elements of the set is. So the cardinality of a set, by definition, refers to the number of elements inside that set. The symbol we use to represent cardinality is n. So n of A is the cardinality, the number of n for number of elements in the set A. Okay, so like that. Given a set A, 1, 2, 3, 7, 23, and 27, we can say that the number of elements in the set is 6, okay? And that number of element is the cardinality of the set. So the cardinality of a set refers to the number of elements in that set, All right, another example. State the cardinality of the set given. So that is called an empty set, and a set that has got no element inside it is also referred to as an empty or a null set. Okay, so how many elements are in that set? Part 2. Set B contains A, B, and C. What is the cardinality of the set? Well, set A has nothing inside it, so it's an empty set or a null set, and so the cardinality of set A has to be 0. Okay, there is no element in set A, so the cardinality of the set is 0. Set B has got 3 elements in it, and so the cardinality of set B is 3. I hope this is very clear. If not, please let me know and we can go through it again. It should be straightforward. Let's move on then. Here's an example number 2. Here is another set, right? I asked a student of mine to describe a common property of this set, and what they said is, what the student said was that they are all disgusting. So disgusting is is a common property for him to all this. Well, I don't see them disgusting. They look really, really beautiful. God's creation, that is. So a common property could be they are all crawlers. Yeah, they have antenna. They have 6 legs. All right. Do they all fly? Well, ants can fly. It depends on which type of ant we are talking about. All right, and so think about all those there are so many common properties. And then the question is, what is the cardinality of the set? So the cardinality is just the number of objects or the number of elements in the set. And if we look at this carefully, I think there are 9 of them. And then there is a second question. Now I bring in another object in the set. There is another one. And the question is, does the added element fit into your description? The description you gave for a common property here, does adding this new element here change your description? And if it changes the description, can you adjust your description so that whatever you have applies to all the elements? So if you said something like they are crawlers, then the description does not change. But if you said they were 6-legged insects or animals, then your description is going to have to change because the spider there has got 8 legs instead. Okay? Let's move on. Here's another example. Yeah, there is an elk having fun. And here's my example. A set V is described as vowels in the English alphabet. So that is the set V. So E for elk is a vowel in the English alphabet. The question is, state whether or not the following are elements of set V. Express your answer or your statement in mathematical notation. So use the notation we've discussed already to try and categorize these objects as to whether they are in the set or they are not elements of the set. So we have B, C, E, I, K, right? You can pause the video and decide whether these objects here are in the description stated for set V. All right, I've put the answers up here, assuming that you've done it already. The vowels in the English alphabet are given there. In the Swedish alphabet, I think there are 4 more, just for context, in case you're trying to find this out. In Swedish, I think there is also that. I'm not even going to bother pretend to be able to pronounce this. So there is that. There is A with an O on top of it. Then there is an O with 2 dots on it, and I think there is a Y also. And all these have got different pronunciations. So these are in addition to what we already have here. So in the Swedish alphabet, you have 9 vowels, okay? So the question is, do these belong in that set, and how do you represent that in using the notation for sets that we've already talked about? So we can write here already that B is not an element of set V because B does not exist in there. So it's not an element of the set. C is also not an element of set V, but E there is an element of set V. I is an element of set V, but K is not an element of the set. Okay, I hope you got that right. We can move on. And now we want to describe what a subset means. So the symbol for subset is given here. What do we mean by a subset? Right? A set P is said to be the subset of another set Q if all the elements in set P are also in set Q and all the elements in set Q are also in set P. So if that's the case, then P is called the subset of set Q, and Q is also referred to as the subset of P. Like this, we write that P is the subset, so that's the symbol for subset. So P is a subset of Q, and of course Q is also a subset of P. We can show this using what we call Venn diagrams. If the two sets P and Q are such that P is 1, 2, 3, 4 and Q is also given by 3, 1, 4, 2, you can see all the elements in P are in Q, right? And all the elements in Q are also in P. So effectively P and Q are referring to the kind of the same set, except they are not the same set because they are two sets of objects in different physical places. So we don't say that set P is equal to set Q. Instead, we say that set P is a subset of Q and Q is a subset of P. All right, we can show this in what we refer to as Venn diagram like that. So if P represents all the elements 1, 2, 3, 4, and Q also represents the elements 1, 2, 3, 4, then 1, 2, 3, 4 must be in both sets, and this is how we represent that. Okay, so if we have this scenario where all elements in P are also in Q, all elements in Q are also in P, then we say that P is the subset of Q and Q is the subset of P equally. All right, but we also have something called a proper subset. So this is called a subset, but we also have something we refer to as a proper subset. Okay, so what is a proper subset? This we've already discussed. So what is a proper subset? Okay, and now the symbol changes when we are referring to proper subsets. So P is said to be a proper subset of Q if all the elements of P are in Q, all right, where Q is a bigger set and P is a smaller set, so all elements of P are in Q, but not vice versa. Not all elements of Q are in P. All right, we write, so we are saying first of all, if the elements of set P are also in a bigger set Q, then P is a proper set of Q, but Q is not a proper set of P. All right, we say P is a proper subset of Q, and here is an example. Suppose set P contains the elements 2 and 4 and set Q contains the elements 1, 2, 3, 4, then clearly 2 and 4 are also here, 3, 1 are not here, so P is said to be a proper subset. P is in Q, but Q is not in P. We can show that on a diagram as well. So if that is set Q with the numbers 1, 2, 3, 4, and P contains 2 and 4, I could draw a circle that encloses only 2 and 4, and you can see set P is completely inside set Q. In that sense, P is a proper subset of Q, but Q is not a proper subset of P. Okay? So we've already talked about this, just writing it down. So Q is not a proper subset of P, but P is a proper subset of Q. All right, let's move on. We are coming to the close of this. Let's list all the subsets of Q here now. Which are the subsets? Which are the possible subsets of set Q here? All right, so if we can create a small set out of this, Which small sets could we create? All right, here we go. We already said that 2 and 4 are a subset of Q. All right, set P contained 2 and 4, which was already a subset of Q. But which are the other possible subsets? Which other smaller sets could we draw out of the set Q? All right, so first of all, we need to know that the empty set is always a subset of every set. So as part of the subset, a set that has nothing on it is a subset of set Q. So the empty set, which is just those two brackets by themselves, no element inside, is referred to as, is actually a subset of set Q. This is something we learn in set theory. So we are just at the beginnings of set theory, really, and we will learn that the empty set or the null set is a subset of any set. Okay, so that's the first subset that we can draw from there. So the alternative symbol that we use for an empty or null set is the O with a slash on it, like that. And so the empty set is, we are listing all the subsets of this set Q here. So the first one is that empty set. Then we can have a set that contains only 1. We can have a set that contains only 2. We can have a set that contains only 3, and one that contains only 4. Right? Then we can take the set, the elements in pairs. So we can have a set containing 1 and 2, one containing 1 and 3, and 1 and 4. We can have a set containing 2 and 3, and 2 and 4. And we can have a set, so 2 and 4 we already found earlier. And then of course there is 3 and 4, right? We can now take elements in groups of 3, and we have one containing 1, 2, and 3. All right, we can have a subset containing 1, 2, and 4, and we can have a subset containing 2, 1, 3, and 4. Okay, 1, but you now leave out the 2 and you take 3 and 4. And then of course we can have 2, 3, and 4. Please learn how to draw out the subsets out of a given set. The best way to do is to start with the singles like that, then try to pair them in, put them in twos or in pairs, and then in threes like that. So if you go in the correct order, you will be able to find all the potential subsets or the possible subsets of a given set. So 2, 3, and 4, and of course there is a subset that contains all the elements. Okay, so then these, if you check, there should be no other subset that we can draw from here. So if we count this, how many are they? You should be able to see that there are actually 16 subsets of set Q. Okay, so there is a total of 16 subsets of set Q. All right, now let's move on. I want to define one more time before we stop, and that is the power of a set. Okay, the symbol for the power of a set is the P, lowercase p, and then you put into bracket and the set name or the set symbol. Okay, so the power of a set Q is a set. So the power of a set refers to a type of set which contains all the subsets of the given set. So in the previous section we just determined the subsets of Q. So all these subsets, if we put them in a bigger set, put a big set and put all this as though they are elements of that bigger set, they form what we call the power of the set. So the power of this set here refers to a set containing all this. So I need to put a squiggly bracket just like this, and then put this set there, put that set like that. So if I put all this as elements of one set, they form the power of set Q. Okay? So the power of a set is a set that contains all the subsets of Q. The power of set Q is a set that contains all the subsets of the set Q. Okay? There it is as the definition, and we're going to see this better. Here's an example. Given a set Q contains elements 3, 7, and 9. Okay, what is the power set, the power of the set? So the power of the set will have the null set, then it will have a set containing just 3, then just 7, then 9, we've taken them in singles, then you take them in pairs, so 3 and 7, 3 and 9, and 7 and 9, and then the last one is going to contain the 3 of them. And if we count all of them, we should be able to see that how many are they? There should be 8 of them there. Okay, so the power of the set contains 8 subsets of the set Q. All right, so the number of subsets in the power set, so in this case the number of subsets is 8. The number of subsets of the power set is expressed like this, like with a modular sign, and in this case the number of elements, it's called the number of subsets in a set. So in this case the number of subsets of this particular set is actually 8. Okay, so P of Q modulus is actually equal to 8. So P of Q modulus refers to the number of elements or the number of subsets that make up the power of a set. Okay, let's see, I hope you got that, but if not, we're going to see more examples here. A set P is defined as the set, so here this is an example, a solved example. Set P is defined as the set of all prime numbers that lie between 0 and 10. The question is, so prime numbers, first of all, in case you didn't know that, prime numbers are any number that is divisible by 1 and by itself. Okay, you can also say that any number that has got only 2 factors, one of the factors being 1 and the other one being itself. So 3 has 2 factors, or 2 numbers that can divide it is 1 and 3 itself. So it has got 1 and 3 as its factors. Okay, that is a prime number. So set P contains such numbers, such prime numbers, but they lie between 0 and 10. All right, the first question I think is for you, write out the set P. So pause the video and write down the prime numbers that lie between 0 and 10. If you've done that right, you should know that 1 is not a prime number, just in case you wrote it down, because it fails the definition that we just gave for prime numbers. So 1 is not there definitely. Also 9 is not there in case you had written 9, because 9 can be divided by 1, it can be divided by 3, and it can be divided by 9. So it has got 3 divisors or 3 factors. Because of that, 9 is not a prime number in case you had written it down. And so which are the prime numbers? They're going to be 2, 3, 5, and 7. Okay, part B of the question says find the cardinality of the set, so the number of elements in set P. Well, from what you can see there are 4 elements in set P, so the cardinality of the set is going to be 4. Okay, part C is asking for the number of elements. Find the number of subsets in the power of the set. So I've decided to ask this question first before looking for P of capital P there. All right. So first of all, we want to know how many subsets are there in numbers. How many are they going to be? And if you understood what we discussed earlier, or if you like, you can go ahead and try to generate all the subsets of set P there, and you should find that there are 16. And so the answer to part C is going to be that the number of subsets in the set P is going to be 16. And lastly, the question is to find that. So find the power of the set. So this means list all the subsets of set P. Okay? And if you do so, I have done it, the set of all the subsets. So if we do that, this is the set of the subsets. 0, 2, 3, 5, 7, then we have 2 and 3 in one bracket, and 2 and 5, and so on. And if you count them, you should see that there are 16 of them. So this is how we find the power of a set. So notice that this symbol refers to a set. So when you're asked for this, you must list all the subsets. But if you're asked for this one, the one with the modular sign, it's referring to the number. How many are these subsets? And if you count that, you should find that there are 16 of them. Okay? All right, here is a problem that I want you to try out. Says, for each of the sets S shown below, find the cardinality of the set, find the power of the set, and then find the power means the power of the set means list all the subsets, and then find the number of subsets in the set itself. Okay, so one of the questions is S, which contains A, B, and C. Part B is the null set. How many elements are there? What's the power of the set? And how many subsets are in the set S? Okay, C is actually described. Set S contains odd numbers that also are prime and lie between 0 and 10. All odd numbers that are prime and lie between 0 and 10. So if you can list those elements of that set, you should be able to find the cardinality and the power of the set, plus the number of subsets in it. Okay, D is described, the set is described as factors of 12. Factors of 12 are numbers that can go into 12, right? Or that 12 can divide. So for example, 1, 2, 3 is a factor, 4 is a factor, and so on. And the numbers we are looking for must lie between 1 and 12. Okay? So try that out. Here's another one that I want you to try out. Below is a set of chessboard pieces. We will refer to the set as C. Identify the pieces by name. Hopefully you play some chess and you know the names of these. Otherwise you can search for the names. And lastly, find the number of subsets that would be produced by this set of chess pieces. Okay? Another one says P is the set of 8 planets orbiting the Sun in our solar system. The question is to find the number of subsets we could get by grouping the 8 different planets. How many subsets can we have of the 8 different planets? Please notice I've not mentioned Pluto because Pluto is not thought to be a planet. It doesn't share the same property that these other planets have in order for Pluto to be referred to as a planet. Huh? Okay, so that's another example. Here is a micro investigation. I will give the answer at the very end, but here is an investigation, and we want to find the power of the set. We want to relate the power of the set, the power of a set, and the cardinality. Okay? Complete the table by first generating the power of the set. Okay? So we have set A. This is an empty set. So here is an example. Set A. Here, the second column will write the cardinality, and in the last column we'll write the number of subsets it has. Okay? So for example, the empty set has no element inside, so the cardinality is 0, and because of that, you may not know this, because there is only one subset, which is the empty set itself, so we will write 1. Okay? This set here contains one element in it, so obviously this would be a 1. But what would be the number of elements or the number of subsets? Okay, the next one has got 2 elements, so obviously this is going to be a 2. But what is going to be the number of subsets we can generate from here? So you will need to first of all generate the subsets and then write the number that they are here. We've already done with the 1, 2, 3, 4. I think we did it with 4. So when there are 4 elements there like that, we showed that there are 16 subsets. Okay? Yeah. This one has got 5 elements in it. So how many subsets? So I want you to fill up this table, and we are going to use this as a mini investigation to find a relationship between the power of a set and the cardinality of the set. Okay? So please try that out, and we will see what you get. I will give the answer to this towards at the very end. And we have now reached the end of this first video, or this first lesson. This is going to be the end of part 1. After this, we'll be going into Venn diagrams. So this is the last part of sets, Venn diagrams, and number types. Particularly, we've talked about sets there. You will find this discussion, questions related to this discussion in the eWorkbook number 4, which I'm going to attach in the comments section, okay? Other than that, then this lesson comes to an end. But before we do that, I am giving the solution to the mini investigation. Okay, so after that, then the lesson ends, and we'll see you in the next video. So to solve just that mini investigation, all right. So the first column, we were given the empty set. Then there was a 4, 3, and 4. 1, 3, and 4, 1, 2, 3, 4, and 1, 2, 3, 4, 5. I thought I saw a 7 somewhere, but it doesn't really matter. So the number of elements in this set, if you did it correctly, you should have found 0. I think we already identified that and wrote it down, and the power of the set was 1. The second one, there is only one element inside it, and if you check for the number of subsets, it's going to be one of the subsets is going to be the null set, and the next one is going to contain the 4. So there are 2 of them in there. Okay, so there are 2 subsets. What about this one here? This is 3 and 4. So the first subset is going to be the null set. The null set is going to be the first one. So we have a big set containing the subsets. The null set is the first one. The next one is 3, set containing just 3. The next one is the set containing just 4. And the last one must be the set containing 3 and 4. So we can generate these 4 subsets. So clearly there are 4 subsets when we have 2 elements in the set like that. Okay. And so the set containing 3 and 4 has got 2 elements in the set and 4 subsets. The set containing 1, 3, and 4 has got 3 elements, so that's the cardinality, and the power of the set is going to have 8 subsets in it. If there are 4 elements in the set, then there are going to be 16 subsets. Okay, if there are 5 elements in the set, I hope you've tried this out. If there are 5 elements in the set, then there are going to be 32 subsets of the set A. So the question then is, predict the value of, in other words, the number of subsets if the cardinality is 7. I'm pausing the video for a second and think about what the last column is going to be. If the cardinality is 7, what is that last column going to be? And if you've checked carefully, you should see that that is going to be 128. Okay, should be, if it is 7, then this column is going to be 128. Okay. Next question is, suggest a formula that relates the number of subsets and the cardinality of the set. Okay, and if you do this carefully, I hope you try and do it. If you do it carefully, you should have found that the number of subsets is related to the cardinality according to 2 to the power of n. Okay, so if we had if there are 10 elements in the set, then it's going to be 2 to the power of 10, which is 1024, and so on. If there are 8 elements there, it's going to be 2 power 8, which I believe is 256. 256 if I'm not wrong. Okay, and so on. So this is the relationship between the number of subsets and the cardinality of the set. Okay, this brings us to the end of this lesson. If you have any question for me, please don't hesitate to ask it. If you have comments, please put it in the comment section. Please remember to like the video. That way it reaches more people. Remember what we've discussed about what we do with these videos. We want them to reach as many people as possible, some of who have no other way to access a teacher, and so we want to try and help them as much as possible. Okay, share the video with anyone else who might whom you think might find it useful, and if you are seeing this for the very first time, please consider subscribing to the channel. All right, thank you very much. I'll see you in part 2 of this discussion.